So today we're talking about modeling exponential growth so that you can follow along with some application questions working with exponential equations. Now specifically we're talking about growth here, and that is populations or different quantities that are growing, that are increasing in size. Now the prerequisite skills. I'm assuming at this point you're feeling relatively comfortable with your exponent laws, although we're not relying on them too strongly right here. And I'm assuming as well that you have managed to work through your compound interest. There's a lot of similarities right there, as compound interest is one of the examples that covers exponential growth. Now, there are similarities between this equation and that equation when you've worked through with compound interest. You will see as we head along. If I am working with this equation, now I'm going to expand this. I'm really not allowed to expand this, but I'm going to see what it would look like if it were expanded right here. This t is merely telling us how many times this b value is multiplying by itself. So really, I could write this as a times b times b times b times b, and it would continue on forever as many times as we have this t value. Now, am I allowed to do that? No, not really, but I'm hoping you can see the impact of that t value right there. Now that is, if I'm looking at a certain population, it's going to start with an initial population a. And we can see that in our equation. If we have not had any days go by, then this is just going to be the amount. That is, if our t equals 0, then our population, which is y, the population at any given time, or the modeled population, will simply be equal to a. That is, b will never show up. But for every time t that's going along, so this is the time of the population growth, for every time t that happens, we're multiplying by another b. So that is, on day 0 or time 0, we would have this. After one time period, a times b is our population. After two time periods, a times b, and you'll see as we go along. So really this b value is the growth rate that we're working with right here. And you'll see that in action as we go forward. So example 1, a bacteria population can be modeled by this equation. P equals 150 times 2 to the exponent t, where t is the number of days. Okay, so they're telling us already what is our period it takes in order for this exponential equation to be modeling our work here. Now the initial population of the bacteria, we can always see, again, that's just the a value. So in this case, that's whatever is multiplying by our power. So here it's just 150. So the initial population, the population before we start modeling, the starting population is 150. Now the population of the bacteria after 8 days, well, we know t is the number of days that we are tracking right here. So if we're tracking and we're working with 8 days and we're working with t equals 8, well, that's fantastic because we have an equation that we can use to model this population. So we can work with p equals 150 times 2 to the exponent 8. Fantastic. Now, if we're doing that right here, make sure you're following your bed mass. Make sure you're evaluating that exponent, that power, first before you work through and perform your multiplication. So we're working with 150 times 2 to the exponent 8. I can just throw that right into my calculator. 2 to the exponent 8. I'm working with 256. So 150 times 256, I can throw that into my calculator as well. And I'm working with 38,400. That's what we're working with right here. Now, next we're working, and this is where we can see really how this equation comes together and works for us. We can see we're trying to find out how many days it takes for the population to reach a certain amount. Now, if we're tracking that, all we're really doing is we're saying, okay, if this is our general equation, we're working with 150, that's our initial population. We're working with 150, that's our initial population, and we're asking ourselves, okay, how many times will I be multiplying it by 2 in order to get 153,600? Well, luckily that's relatively straightforward to do in a calculator. We're just going to perform some repeated multiplication, right? So we're working with 150 times 2 to the exponent t, except this p we know already that we're looking for is 153,600. So we'll throw this into our calculator. Okay, 150, and then I want you to hit your equals button. And then we're going to type in times 2. and we'll hit equals again, and that should be our population after 1 day. Okay, now after another day, we multiply it by 2 again, so we just hit our equal sign again. That's after 2 days now. After another day, I'm going to hit my equal sign again. That's 3 days, 4 days, 5 days, 6, 7, 8, 9, 10. There we go. There's the number we're looking for, and we can see that 150 times 2 to the exponent 10 through performing some repeated multiplication. That's what we did with our calculator. We performed some repeated how many days it would take. So therefore, it takes 10 days. Now, our next example, nice and straightforward. This actually is an example that you have seen in another lesson when we were working with our compounded interest. Now, we're just seeing this laid out in a slightly new way, only really that we're looking at it from a new lens. So now we're looking at this from a population growth perspective, or from an exponential growth perspective, and we'll work right here. Okay, how much money was originally invested? Well, what's another way of saying originally invested? What we're really looking at is the initial investment, the initial amount. The initial amount is just given to us right in the equation. That's $2,500, nice and straightforward. How much will Pam have after 30 years? Okay, well, we've been given this equation already. So all we're doing is substituting in the value that we know, 30 years. We're working with t equals 30 because we know t is the number of years. Nice and easy. So we're working with a equals 2,500 times 1.05, because there's a 5% interest rate, to the exponent 30. Nice and easy. Make sure you follow your bed mass. I want you to pause the video here, unpause, and see how you did. Good, so we're working with $10,804.86. And lastly, we're going to again perform some repeated multiplication. We're going to work with our equation. A equals 2,500 times 1.05 to the exponent t. We don't know what t is. We need to find out what t is, but we do know some pieces. We do know that a is equal to, whoops, I got rid of my equal sign. A is equal to 8,062.75 cents. Okay, so all we need to do is find out what this t value is equal to. I want you to pause the video, try it out yourself. We work with 2,500. We multiply it by 1.05. That's after 1 year, 2 years, 3 years, 4 years, 5, 6, 7, 8, 9, 10. We're performing our repeated multiplication until we get the number that we need. We're looking for 8,062.75 cents. Look, 24 years. Fantastic, because we hit that equal sign 24 times. So we're working with 2,500 times 1.05 to the exponent 24. How did we get here? We performed repeated multiplication. Good, so if you followed along here, I suspect you should be feeling a little bit more comfortable to work through these practice problems, and hopefully you're feeling a little bit more comfortable with what exponential growth really is. Nice work.